Okay, time is 10:40 in Sweden and Norway, so I will leave the the screen and the stage to the team from COWI who's going to talk about a special bridge. So please, Aitor and Anne-Marie, please, I leave the word to you.
Yeah, thank you, Frederik, and hi everyone out there. It's good to be here, and we are happy to present the 1915 Çanakkale Bridge, which you can see on the image is a suspension bridge. It's located in Turkey, and COWI did the detailed design. The presentation is about how the modeling was handled in Tekla and the development it led to. And as the work we did was carried out in 2017 to 19, many of the processes would be different today, but the principles are still the same. Aitor. My name is Anne-Marie, and I am from COWI, and I have been there quite some years and is working as a PIM specialist.
Hi, I'm Aitor Gurruchaga, also working as being a specialist in COWI. I have been in COWI for 8 years now, and I'm a building engineer as a background with a master in building management and civil engineering. Agenda for today, Marie will introduce the bridge to all of you, describe the scope of work, and talk about the different structures. But we will focus mainly on the suspended deck. And at the end, I will talk about future development.
Yes, so I will give a little introduction to the bridge itself. And here you can see where the bridge is located in Turkey, as said before, and around 200 kilometers southwest of Istanbul, crossing the Dardanelles Strait at the south entrance to the Sea of Marmara, and it is the only route to Istanbul and the Black Sea in the north that you can see in the smaller image. More than 40,000 ships passes every year, and in addition to that, the bridge is furthermore located in an area with high seismic activity and with large wind impacts from the Aegean Sea. So there has been a lot of challenges in the design. Next, please. Here are some numbers for the bridge. The bridge has a main span of 2,023 meters, which is not only the longest span in the world, but also the 100 years anniversary for the Republic of Turkey. There is a lot of symbolism in the bridge, as it is the location for a battle that took place in the First World War in the year of 1915, which also is a part of the name of the bridge. The towers are 318 meters high, which also is a date for the victorious battle that was on the 18th of March. The main cable, the suspension cable, has a diameter of 870 millimeters with 144 strands, and the highest point of the deck is at level 86 meters. Next, please. Our client were the consortium GLSY, which consists of contractors from both Turkey and South Korea. And our scope were the detailed design together with a consultant from South Korea called PEC. There were no requirements for 3D models or any other information rather than drawings and bar bending schedules. The drawings were supposed to be submitted in PDF and AutoCAD format. For the structures we did in Tekla, they got RFC files per request, but it was for information only. After the design were completed, COWI got the contract for construction engineering for the deck erection, and it was a huge benefit that we had the 3D models. Here you can see the different parts we did in Tekla. And as it was one of the first major bridge projects we did in Tekla, we didn't use Tekla for all structures. We did the concrete structures, the anchor block, the sidespan pier, and the tower foundation with full reinforcement as it was necessary for creation of the bar bending schedules. And then we did the suspended deck, which you can see on the top in Tekla, and it is a steel structure. We started out having everything in one model in Tekla model sharing, but we decided after some months to split the model into models for each discipline. The reason was that the model became quite heavy, and we were around 20 modelers, and it was a lot of reading in and writing out, especially around submissions. So, and furthermore, the risk of if something went wrong in the model, it was minimized with having different models. So, next, please. Now, we will focus most on the suspended deck, as the way we model the deck has led to a development project that Aita will talk about later. The bridge deck is a twin box girder with a cross girder in between, and is 45 meter wide and has 6 traffic lanes. The height of the deck is 3.5 meter. Everyone might not know exactly how a suspended deck looks like, but the deck is divided into segments, typically corresponding to the distance between the hangars, and you can see what is selected in the image. That is a segment on one of the boxes. The segments are constructed in fabrication yards and then transported to site and erected into place. A deck segment consists of an outer box, including the stiffeners, the longitudinal steel, transverse diaphragms, and a hanger anchorage, and between the two boxes, the cross girder. Next, please. So there were some considerations how to do the modeling, and the developer came up with the idea of having dummy beams to control the geometry and setting out. An object based on a parametric profile that represents the geometry of a deck segment, both in transverse and longitudinal direction. Those dummy beams were main parts used to insert the actual objects. The segments are straight, 24 meter long, and got inserted into the model in the curvature that defines the longitudinal profile of the bridge by start and end coordinates exported from our internal analysis software, IPDAS. This approach has been developed further with a live link between IPDAS and Tekla, so IPDAS inserts the dummy beams. Throughout the life of the model, the dummy beams continue to be useful, as each face and corner could be used as reference for setting out for further modeling. And you can see the 2D picture with WP1 and WP2, that there are some working points, and that is what is related to the dummy beam. Yeah, thank you, Aita. All the main parts was prepared as custom components and inserted by utilizing the dummy beams. And you can see it in the video how that is happening by picking the object. This is now a more automated process with grasshopper scripts and inserted as grasshopper components, which I also will talk about later. It was taking into account all parameters that varied, so it was possible to update the parts individually. Next, please. Yeah. So here is another component, which is the diaphragms. They vary in types, and we had different components to accommodate for that. Within the component, it was still possible to have individual parameters when needed. And the top image is the typical diaphragm, and the lower one is at the cross girders. And in between, there are also different types. It got inserted relative to the insertion points of the dummy beam, and had a variable to define the distance to the location. Typically, there were 6 in a segment. Next, please. The components for the hanger anchorage and the cross-girder followed the same principle. The advantage of having the different parts as components is that you easily can isolate the specific elements that belong to a certain part rather than having individual objects, and it helps also in filtering on the drawings. And here you can see the hanger anchorage, and to the next one, please. There you can see the cross-girder. Yes, there were some areas where the modeling were done manually because it was unique. There were no repetitive in that. So, and it was around the tower, which is the one to the left, and at the bridge end. And here it was very beneficial to have the dummy beams, as a corner and faces were used to place the manual modeled objects. Then we were ready to do the drawings. No, please back one, Aita, still. For the whole project, we did around 1,700 drawings. There were a few done in 2D outside the Tekla environment, but most were derived from the Tekla models. It went fairly easy after we considered the filtering to avoid seeing too much on the drawings and having double lines. Now we can switch. After the design of the tower foundations were completed, we got a request for an optimization that could speed up the construction and reduce the amount of offshore works. Next, please. In brief terms, the process for the tower foundations is that most is cast in the docks, filled with water, tower to side, and then immersed into place to be finalized on the bridge location. Instead of having formwork and reinforcement in situ at the bridge location, a solution based on prefabricated cages containing all formwork and reinforcement were introduced. Next, please. The tower leg is composite with steel skin plates, and you can see, on the right picture, you can see the cages with the reinforcement. And the tower leg is composite with steel skin plates and concrete cast between, which you can see on the upper left image. And the leg has a diameter of 18 meters. As you might also see on the images, it is rather congested, and the reinforcement from the cages should fit into the tower leg, where there were a lot of shear connectors, and it was a struggle to make the reinforcement fit. We didn't have much time to do this, so design, analysis, and modeling were done at the same time, and in close collaboration with the contractor, of course, that followed it very carefully. So we immediately were able to adjust the design if needed. Luckily, it all went well and would have been hard to achieve if we didn't have the models. Next, please. So another extra work was that COWI did the construction engineering for the deck erection, but I will not talk much about that here. On the image, you can see a deck segment is lifting, and we did segments that were 24 meters long, but it's the lifting capacity. They were able to lift 48 meters, so they actually lifted 2 segments at a time. It was a fast track, and again, it was very useful to have the 3D models. Thank you, and now I will leave it to Aita to continue.
Thank you, Marie. Okay, so future development. So now the bridge is built and we need to look for the next steps. So what are we going to do if we need to do another Çanakkale or similar kind of bridge? So we started to think on some development in that regard. So if that's Tekla link, we look how we can connect our internal analysis software with Tekla. So before I talk about the link, a quick look on IPDAS. It's our parametric analysis software developed by COWI on the 80s, and provides us high detail 3D models, and also, and it was used at its bridge and the Great Bell link, and in any more, a lot of different projects, but this one is quite famous in Denmark. These are some of the type of models that we can create with IPDAS. The one in the bottom is for analysis and calculations, but the most important one for us is the one on the top, and is the geometry model that we want to transfer to Tekla. So we managed to get the link between IPDAS and Tekla in place. How? But through the Tekla API, we asked to our development IPDAS team to code and develop the integration. And why? We saw the benefit to have a single point of truth, that we call it a spot, as the geometry and the analysis were both connected and coming from IPDAS. And that will always help us to avoid repetition, because we don't need to model in Tekla what is already done in our analysis software. So with the link working and in place, we started to think in our new workflow. We will have a single point of truth with the design information. It will go into IPDAS, and then the geometry model will be exported into Tekla. And we will use Grasshopper to generate the different structural elements. The beauty of the workflow is that it can be used without IPDAS if it's not a requirement. It can be used with IPDAS and other different analysis softwares as well. So at the end of the session, I will show you other structures types that can be, or they use the same workflow, but now we will focus on the deck. So similar to what Marie described before, we will export from IPDAS some elements into Tekla. We will call these elements dummy beams. They are information containers that will define the geometry and provide all the information needed to model the steel plates. These dummy beams are native elements in Tekla, such as beams with a parametric profile defined in the sketch editor. This is just an example of a bridge that is exported from IPDAS into Tekla, and then on the left you can see the UDAs also coming from the design input. So after the dummy beams are in place, we will run a Grasshopper script that read the UDAs and create the plates. In this case, we will not run Grasshopper directly. We will use Grasshopper components, as allowed us to run the script without being an expert in Grasshopper. So why Grasshopper components? As you can see on the videos, the Tekla user can create the structural elements in a really easy way, just after a few clicks. On the left, we are creating the diaphragms. And in the video on the right, you will see, after clicking on the Grasshopper component, that how we create the longitudinal steel. So one great advantage of the development is that the elements generated are, as we said before, steel plates. So they are native elements in Tekla, giving us the opportunity to edit them manually in case we don't need Grasshopper. So more or less on the pictures, we are trying to show that which UDA is inside of all the elements that are created. This is just a quick diagram of the workflow. And this video is a demonstration of the workflow itself. So the Tekla user only needs to open Grasshopper component application and run the Grasshopper script. You can visualize it if it's needed, but you don't need to be an expert in Grasshopper to use the component. This is just in case you want to check what the Grasshopper script is doing. So as you can see, after few clicks, we just select the component, we select the dummy beam, and then the rest of the elements, the different plates, are modeled in Tekla. Oh, now we are cleaning up a little bit but here it is, the result. So this is other structures, or other structures that we think that the workflow can be implemented, and we hope in the future to use it. So not only for the deck and the diaphragms, but also the cross girder and the tower segments. So now I'm going to talk about the workflow for reinforcement concrete. As you can see on this diagram, we apply the same principle that with the steel. So we use the Grasshopper components. The biggest difference in this concrete or reinforced concrete workflow is that they are exported directly from IPDAS as a concrete item. So they are not dummy beams. It's the final geometry imported in Tekla as I said before, as a concrete item. This is an example of inserting the component. In this case, we click on the Grasshopper component, we select the concrete item, we indicate what is the direction of the reinforcement, and then all the magic is happening. In this example, we show how we can manipulate the information inside the elements in case we don't need to use Grasshopper or if we want to do the changes manually. So basically, we can see how the top reinforcement inside the concrete will stick out of the concrete after applying the new information. Yeah, that's it. Thank you very much.
Thank you very much, and also on time. I see we don't have any questions right now for the session, so everything was clear and professional. I just wait 1 minute if it pops up a question. Otherwise,
okay.
No.
Okay. No, there was a question, but it's something else, no?
Yeah, well, yeah. Okay, now I have a question. I can read it for you. What value do you see of using components instead of pure GH? Or Grasshopper?
Pure Grasshopper?
Yeah.
And Marie, you...
Yeah, as I think it's very nice that you can, if you take the box girder we showed before, I think it's very nice that you can when you do the design, it's also based on different parts of the segment. So you have the longitudinal steel or you have the diaphragm, and then I think it's very nice that we can isolate that by having the Grasshopper components, and because you need to submit or maybe you need to submit information, attributes, or other information, and that is related to certain parts of the bridge. So it's an easy and nice way to isolate things.
Mm-hmm.
It's one of them.
Yeah. Also, I think we tried to say in the presentation, I think if you are not an expert in Grasshopper, it's a really nice first step to introduce you to the workflow, because maybe you are a little bit afraid to open the script, I don't know, manipulate it, change something. With the Grasshopper component, yeah, you just run the script, but you cannot edit it. There is no risk of doing anything wrong, let's say, or we minimize the risk, I think, from the Tekla user, from the end user.
Yeah, we have another question, and we have the time. So, did you provide 3D to contractors, for example, survey?
No, we did not. as they got the IFC files of the different structures, but it was for information only. So I think in when we did this redesign I showed, there it was a value. It was value, but I don't think it was. They only used it for visualization.
Yeah, at this point, we didn't have too many requirements for the 3D, so we did the bridge or the design and the modeling in order to learn. So it was one of the first bridges we did in 3D of this size, for sure.
Yeah.
I received one more question. If you were doing this job today, would you produce? No, okay, now it's jumping here.
Oh yeah. But this is for another. I think this is from the previous.
Oh, okay. But here we have one. It arrived 4 times, so that's the reason. If you were doing this job today, would you produce constructible models then?
So I think we would do the models we would do would be to the reference condition of the bridge, which, if that makes sense, because of course when you have a suspension bridge, it has different stages and so the level we would do it to would be to the reference conditions, which means the I don't know how to say it, the theoretical numbers. But of course, we would have a collaboration with the contractor and what he, if he had some request, we would try to fulfill that and accommodate with that.
Yeah, that was about to add a little bit more. Is that probably we will depend a lot of the requirements from the client. So yeah, if constructible model means that, yes. If it's model, I mean, we always build the bridge or design the bridge to be constructible. Of course, as Marie said, we define or we design the how you say, the theoretical design of the bridge. We don't consider if the bridge will move, I don't know, or there is a deformation due to the wind. We don't model that kind of changes right now, at least.
But good question, good answer, and I would say thank you, Aitor and Anne-Marie. It was a very good presentation. And now in 6 minutes, we will have the new presentation. So stay tuned, and we will soon be on the stage again.
Yeah.
Thank you very much.
Thank you.
everyone.
Yeah.
Bye-bye.
Bye-bye.